Thank you. I would like to thank the organizers for inviting me at this conference. It's an honor to speak here. Okay, so I will talk about sieve weights and their smoothings. And this is joint work with Andrew Granville. And James Maynard. Okay, so maybe I will start with a little bit of background material. So let's write n is tilde x if n is in the dyadic interval between x and 2x, which is pretty standard notation now. And let's say we want to understand how many twin primes there are in between x and 2x. So I want to count those indices n for which n and n plus 2 are both prime. Okay, so this is a typical sieve problem. And so the starting point of sieve methods is to observe that this can be rewritten as the following quantity. As this count, where m here is the product of primes up to, say, root 2x. This goes essentially back to the Eratosthenes. And so instead of understanding this quantity, let's understand this quantity, which is a combinatorial quantity. So we want to exclude divisibility by all these primes. Okay, and then one observes that if I want to understand this characteristic function, indicator function of the event that A and M are coprime, then I can write this as this divisor sum using Mobius inversion. So I can plug this into my formula. And get an exact identity. And then, okay, well, I'm going to switch the order of summation naturally. So inside we have the number of integers n and n plus n in the dyadic interval x up to 2x, such that n times n plus 2 is 0 mod d. Okay. And now we see this and we're stuck. And why are we stuck? Because these divisors here of m can get really huge. So m here is the product of primes up to square root of 2x, which is about e to the root 2x. And we can certainly not count integers of size more or less x in progressions that are of size even x to the 1 plus epsilon. And for a long time, this is where the subject was stuck till Brun took it into his hands. And Brun's idea was, well, maybe I should replace this exact formula by an approximation of this of this shape, a divisor summation, divisor sum of this form, and this means that this sum should correlate strongly. And the stronger correlation one has, the better results one is going to obtain. And moreover, one should have that Rd is 0 if d is greater than some parameter d, which typically one wants to take to be some power of x And so we want to go from e to the root 2x to x to the little power. And the miracle of Sieve method is that this is actually possible. And nowadays we have many ways of doing this. Okay. And the older way is using combinatorial considerations, going back to Buchstab and to Brun. And these involve taking, so the combinatorial sieve would be to take rho of d, nu of d times, but only supported on some special set d that is defined anatomically. And by this I mean that you look at the factorization of d, and then you throw away, you only keep those integers whose prime factorization satisfies certain nice properties. Anyway, I don't want to get into this because that's not the point of my talk. Because what I want to talk is about Selberg sieve. So Selberg sieve, Selberg started from a very simple idea that says, well, I can always upper bound this quantity, this characteristic, this indicator function here, by a divisor sum of this form. As long as I take a square, I always guarantee non-negativity. And well, when a and m are is actually 1, so that the left-hand side is 1, then let's take lambda 1 to be 1, so that we guarantee equality. And if I plug this into here, I get an upper bound. Okay, sorry. I'm gonna start here. So what is the upper bound? N up to x, and then this summation, and then if I open the square and change the order of summation, I get the summation of d1, d2, and then lambda d1, lambda d2. And this count. And this count now equals x over d, because we split x into intervals of length d, and then we look what happens there periodically. Yes, thank you. And rho of d is the number of local solutions. Okay, so this is essentially the divisor function, because when d is odd, it's and square free say it is actually the divisor function. And then let's just ignore the error term, and to ignore the error term, one should have to assume that lambda of d would be 0 if d is, say, greater than r, and then this leads to a parameter capital D, which is r squared. And so then this takes care of the error term, and the main term is now a bilinear form into the lambda d's. And one has to optimize this. And I have one more board there, so let me use it. Right, so when you go through the optimization process, then the optimal choice is of the form some constant that is normalized, that is due to this condition, that lambda 1 is 1. The divisor, the Mobius function, and then something that looks like, in this case, like this. And I have the cutoff d is only up to r. And in general, let's say I want to count, and oh, by the way, this leads to the upper bound 8 times the truth. Yeah. So 8 times what you would want to prove. So this is the twin prime constant, which is 2 times the product of 1 minus 2 over p, 1 minus 1 over p to the minus 2. Anyway, it's some constant that if you've seen, you know where it comes from. If not, then don't worry about it. One can ask more generally, what if I want to make more, I want to detect larger patterns of primes. Say I want to take a k tuple h1 up to hk, and I want to detect how often all these quantities n plus h1 up to n plus hk are all simultaneously prime. And then in this case, lambda d turns out to be some normalizing constant times the divisor, that is mu of d, and then you have log of r over d over log of r, and then to the k, the optimal choice. And again, only up to r. Okay, so yes.
Is there any clear reason
Why?
why those would be the optimal choices?
Well, maybe I will explain this. Okay, so what I want to observe is that when you want to detect more primality conditions, you have a higher power here, which implies that the decay is done in a smoother way. Okay. Here I only have 2 derivatives, and here I have k derivatives. Well, k minus 1, and here it's actually 1. Something like that. So motivated by, so in general, this kind of, the fact that this kind of weights kind of correlates strongly with all of these objects being prime was a very important ingredient in the work in bounded gaps between primes. And these are the weights that were chosen so that we can detect gaps between primes. And, well, not these exactly, but variations of these, in the work initially of Goldstone, Pinch, and Yildirim, and then by Maynard and Tao in the generalization of these weights. And so motivated by this work, and also by trying to understand better what is going on in the Selberg sieve, let's define this kind of general Selberg type weight. Okay, MF and R will be mu of d, and then F will be this cutoff function, so it will be supported only up to 1. And I also assume that f of 1 is 1 And what this implies is that MF of NR is 1 if n doesn't have any prime smaller than r. So if this is a genuine sieve weight, this kind of integers should be dominating its average behavior. Okay, and then in the work of, well, after the GPY work, Conrens and Rarajan did some analysis with general functions f that are smooth at 1. And also this is how the functions are chosen in the Maynard and Tao work. But why do we need them to be smooth? F of 0, sorry. F of 1 should be, I guess, typically 0. Yeah, thanks. Right. So why do we actually need them to be smooth? It's not, OK. It's true that the Selberg sieve, when you do the optimization process, it gives you a smooth weight. But OK, this doesn't mean that this is the only way that will work as a sieve weight. So let's take an extremal example where we look at, well, yeah, it's like that. It's this function plus 1 over log r times something that this has a smaller smoothing, and so on and so forth. OK, so let's take the sharp cutoff, f that is somehow the most discontinuous natural function that has this support, the simplest such function that is not continuous though. OK, this is 1. And let's ask ourselves, is this a sieve weight or no? And if this is, why don't we just try and use this weight? But there is a very curious thing that happens. Let's consider an integer that is 2 times m, where m is odd. And let's look at what happens to this weight. So m of nr, in this case, I can split this sum into 2 parts. Those divisors that are only divisors of m, plus those divisors that have 2 in them. So 2d. D will also divide m, and D will go only up to r over 2. And then mu of 2 is minus 1, so I will get the minus sign here. And the divisors up to r over 2 are in both sums, and they will get cancelled in the first sum. And this sum now is just a sum of integers, right? Mu of d is only plus minus 1 or 0. So for sure, this will be plus or minus 1 if n, or rather m, has a unique square-free divisor d in the interval r over 2r. Okay. Right? And now the question is, how many such integers are there? And this was answered by Ford. The number of such n is of size, well, Ford's work doesn't answer exactly this, but a small tweak of his work will answer this. So x over log r to some constant delta times log r to the 3/2. And what is this delta? It's this constant given by 1 minus 1 plus log 2 over log 2 which is something like 0.08, and so on and so forth. And what is important, it is less than 1. And why is this important? Because if I say take the second moment of these sums, then I get that this is at least x over log r to the delta plus little of 1. And how many such integers are there? Only x over log r. And if these weights were behaving like the characteristic function of this set, or were strongly correlating with this characteristic function, right? So the number of n up to x such that whenever p divides n, p is greater than r, is like x over log r. And here we see that this weight gets much bigger on average. So certainly this will not be a good choice for a sieve weight. So some smoothing is necessary, and these isolated divisors are one of the. It's a hands-on way to see why. Why it will not. And as a matter of fact, I should say also that the integers that do have a divisor between r over 2 and r have lots and lots of prime factors. Something like log r times a constant, prime factors. So this sum will be supported on integers that look nothing like almost primes. Very, very different. Okay. So we need to have some smoothing in order to bias our weights to only capture almost primes, or something that looks like that. Right. So now let's consider a more general. Let's consider a function that say is in C1, and let's repeat the same construction, but then assuming that our function is in C1. So I will write my n as some prime p to the v times m, where p does not divide m. And I will look at mf of nr. And then I can split the summation again into two parts. Those divisors that only divide m, and those divisors that have p in their factorization as well. So let me skip one step. The mu of dp becomes minus mu of d, and I have here f of log of dp over log r. Okay. So if I combine this into a single divisor sum, I have a difference of two values of f, and I can use the fundamental theorem of calculus to rewrite this as the integral from 0 up to log p over log r. And then the sum inside will be mu of d, and then f of u plus log of d over log of r du. F prime. Thank you.
Sorry, Dimitris,
Yeah.
can you explain again why it's so terrible, this second moment lower bound that you got? Why does that force you to?
Because I'm aiming for a bound of this form, x over log r, and this is bigger.
I see.
These moments will, right, because these weights are 1 on integers that have no small prime factors, these moments are always at least x over log r. And are they at most x over log r as well, is the question. Okay, and why stop there? Let's assume that f has more derivatives and iterate this process. Okay, so assume that f has a derivatives, and assume that n has at least a distinct prime factors. And write it like that. And then if I iterate what I did there, I will find that f of nr is minus 1 to the a, and then I have an a-fold integral. Here I have the summation of the ui's plus log of d over log of r. And I need to integrate over all of these variables. Okay. And if I take absolute values everywhere, it looks like this is essentially again, I'm forgetting the derivative. It looks like it's something like it's controlled by a quantity that looks like this. Okay, and our enemy are integers with small prime factors or with lots of prime factors. And if you have an integer with lots of prime factors, you will have small prime factors. A typical integer does have a small prime factors of size big O of 1. So if n is typical, or if where this is to be interpreted very, very loosely, then essentially a derivatives cut r logarithms, reduce the size by a logarithms. And right, so here I guess the PIs would be the small primes. So Pj would be the j smaller prime factor of n then, for this to work. Okay, so then a reasonable conjecture seems to be, or maybe more of a guiding principle than a conjecture, seems to be the following. So I'm going to take high moments because in order to have abnormally large values of mf of nr, you need to have, in order to, if you see a little bit of smoothing is going to already cut some logarithms, and we'll tell you that the dominant contribution is not coming from typical integers. So if you really want to test this, whether this kind of heuristic is true, you have to take high moments in order to see high values of fn of r, to pronounce the high values and check that this heuristic is true. So we have two competing worlds. We have the almost prime world, which, in which case these weights behave like Sieve weights, so the upper bound is x over log r. And we have the world when these do not behave like Sieve weights, so they're dominated by integers with lots and lots of prime factors. And then what I should be comparing with is the unsmoothed weight. I don't have a lot of space here. Okay, so remember that M and R is the sharp cutoff, where I take my f to be 1 up to 1 and then 0 otherwise. Okay, so right, so and this is the world when you have almost primes. And this is the world when you have typical integers dominating. And there should be some phase transition from one word to the other. As long as you smooth enough, then you pass from one word to the other. So how much should you smooth to make the 2kth moment of these sums behave like a Sieve weight? Well, it depends on how big this sum is. So, and then there is, of course, this looks like a divisor sum, sort of. And so we can expect it to behave like a divisor function. And if it does behave like a divisor function, then it should have an asymptotic of the form some constant ck times x times log of r to an exponent, ek. And then we would need I should say, well, 2k, no, sorry. What is the exponent of the logarithm here? ek minus 2ka to be less than 0, which means that a has to be greater than ek over 2k for the almost prime word to dominate. This will be an integer. Here? Well, yeah, but this is a heuristic rather than a conjecture. It's a soft conjecture. It's a in some cases it's true. Okay. Okay, so now there are two questions that arise. The first one is, okay, what is this exponent ek? And the second one is the conjecture actually true or close to being true? What is ek? Does it even exist? And second one, is the soft conjecture true? So I'm going to start with the second question and then go to the first one. So here is the first theorem. So assume that you have some f that is in CA of R, and assume that all the derivatives are uniformly bounded. And also that it's supported between up to -1. If A is at least e to the k over 2k plus 1, then the following happens. I have this board. Then what? Okay, so I will look at the 2kth moment of these weights, but only for integers that have kind of a small prime factor. So alpha here, think of it as being small. And then what we get is that some saving over x over log r, so even smaller. And this holds when x is at least r, at least 2, and alpha is between 1 and not too small. Otherwise, well, there are no such primes. Okay. So what does this mean is that most of the weight of the 2kth moment is coming from integers that do not satisfy this, meaning all of the prime factors are bigger than r to the alpha for a small enough alpha. Therefore, you have that these weights are genuine sieve weights, do what you would expect a sieve weight to be doing. And also, one can show that you also get if I look at the 2kth moment, then I get an asymptotic formula. Once you have this, getting the asymptotic formula is quite easy. Because then this function is simply a continuous function in at most a primes or something like 1 over alpha primes. And for this, I need more room, something like that, and r going to infinity. And in the complementary case, I guess that would be case A. And then case B would be if A is not so big. Then we still have some upper bound. So not quite the upper bound we were hoping for, but almost. So we only lose something that depends on k, not on a. And also, if you restrict here to integers that have most of the contribution here is coming from integers with a lot of prime factors, constant times log r. The constant depends on k. And in the sense that if n does not have so many prime factors, then you can save even more in the exponent. So this is a partial confirmation of this soft conjecture. But of course, this theorem does not make so much sense if I don't tell you what E of Ek is. I need to tell you what Ek is. Well, we first proved, okay, the proof contains that. But the way I'm stating it, yeah.
Doesn't the second statement on part A indicate that EK is 1? I'm not understanding.
EK is 1?
Well, isn't the second statement the same as the conjecture?
No.
Oh, I see. That's what that, yeah.
Okay. Right, so what do we know about EK? So this is an old problem, and it has been studied by various people. So when K is 1, E of 1 is known to be 0 by work of Dress, Ivanitz, and Tenenbaum. But I believe was done in 83. Yeah. When K is 2, E of 2 is 2, I think. Yes. And this is due to Motohashi from 2004. And for any K, EK exists. And this is due to work of Balazar, Naimi, and Peterman. From 08. And this builds on work of Labretes. So his name should also be here. So what they showed is that these moments have an asymptotic of the form equals x times a polynomial in log r plus a small error. But they don't tell you what the degree of the polynomial is, so they don't really tell you what E of k is. It is, the proof depends on an iterative argument that doesn't really specify. They didn't compute it. They couldn't get it from their proof. Okay, so how would one go about to understand this quantity? Okay, this quantity equals to that. And now if I open the 2kth moment and change the order of summation, and then we have this summation over 2k variables up to r, and then we have mu of d of each one, and inside we have an easy quantity. So this equals then x times the sum of the, sorry. These variables over the LCM plus big O of r to the 2k. So as long as x is a bit bigger than r to the 2k, this is fine. Yes? It should hold for smaller x's presumably, but then it would be much harder to access it.
Presumably it's going to start failing if x is really small.
Yes, for sure. Yeah, so x needs to be at least some power of r, but then exactly which power is not clear. So if you see these bounds here and you compare them, let's take alpha to be 1. We actually know that this is of order x over log r all the way down to for x up to r. Right. Okay, so right, so what do we do with this? We have all these restrictions of the di's being up to r. We'll apply 2k times Perron's formula. So this would be okay, so Perron's formula tells you that this is more or less that, this complex integral, and here I need a bit of room to make this work. I'm ignoring every convergence issue. And right, so what is this function now? So now the variables are all free. So this has has a multiplicative structure, so it will be written as an Euler product. And what will be the 1 over p to the right? So what is important is when this LCM is p, and how can this LCM be p, a prime p? If there is a non-empty set I such that di is p for I in I, and di is 1 for I not in I, right? And then what is this quantity then? It is minus 1 to the number of variables that are p, so to the I. And I get p, and p to the 1 plus the sum of the SIs for I in I. Right. Again, I forgot one board. It's okay. Right. So then what is this product then? What is the summation, sorry? Then I can write it as some benign function f times the quotient of zetas. So whenever I has even cardinality, I get a plus, so I get a zeta in the numerator. And whenever I is odd, I get a zeta in the denominator. And this guy is analytic in some nice, in a wider region. So we can treat it like some constant. Okay, so what do we do when we have such an integral now? This thing has poles. So we start shifting contours around and pick up pole contributions. So let's say I shift the S2k variable to the left. So S2k goes to the left. Where are the poles coming from? Whenever you have some Si being 0 with 2k with I containing 2k and I even of even cardinality, I mean. Of course, you have maybe you have a pole because you have poles here, but maybe some of the SIs vanish in the numerator, in the denominator, so the zeros will the poles here will annihilate the poles here, and you won't have a pole. So, but in general, the order of the pole would then be what? You have to sum -1 to the I over these intervals, right? I non-zero, non-empty, and then containing 2k. And then you also want Si to vanish, right? And then you add with +1 the even i's and with -1 the odd i's. So this is only when you have shifted one variable. And now this variable is gone. And for each of these contributions, whenever one of these linear forms vanish, it means you can express S2k in terms of the other variables. Right, so I can write S2k as some linear form in the other variables. And then I'm left with 2k minus 1 variables. Maybe there are no more poles left, or maybe already this exponent here has vanished, and you cannot really gain any more. You cannot make this quantity be smaller. Or maybe you can still shift, and then maybe shift 2k minus 1. And then pick poles when Si is 0 with 2k minus 1 being in I. And then you have a corresponding order of the pole, which you have to keep track of. And you keep doing this. And let me just also tell you here that when this condition means that that S2k minus 1 can be written as a linear form in the 2k minus 1, 2k minus 2 remaining variables, and therefore also S2k can also be written as such a linear form. So every time you eliminate one variable, it becomes a linear combination of the remaining variables till you can no longer shift contours. So there is a lot of bookkeeping, as you can imagine, and this is, I think, the hardest part of this proof. How do you keep track of all these pole contributions and locate which one is the dominant one? So what happens in the end after, assume we have shifted m variables and there is nothing left. There is nothing left to do. Okay, assume we have shifted. Let's see, 2k minus m variables. Then what happens is that all of the variables Si are linear forms in the first m variables. Sj. Right? Where this matrix will contain some copy of the identity matrix. And what does it mean for Si to be 0, where these are now free variables? So what does it mean for this linear form to vanish? It means that this linear form vanishes. But for a linear form to vanish, it means that all of these coefficients must vanish. Okay, so here is a combinatorial problem. What is the order of the pole? After we have done all the shifting. So the pole Ek then should be what? Should be the maximum over all m. And all these matrices A that contain Im, the m by m identity matrix. And then what would be the pole order would be minus 1 to the I. And then I have I 0 subset of the integers up to 2k. And I want these quantities to be 0 for all j. But I'm not done because I have shifted 2k minus m integrals to arrive here. And this cuts the order of the pole by this much. Okay, so what is the maximum of that is now the question. And this should be Ek. And so I'll give you the answer. The maximum occurs when m is 1. And then when A, this vector here, consists of 1 minus 1, 1 minus 1, 1 minus 1. And in this case, Ek, it's an easy calculation to see that if this is the maximizer, then Ek must be 2k choose k minus 2k, which was an unexpected answer to us at least. This is a theorem. Yeah. And yeah, so this is a theorem, so maybe I should call this theorem 2. And you can check that when k is 1, this is 0, and when k is 2, this is 2. Okay. By induction, it works. And I should say that this proof only detects what is potentially the largest power of log r in the expansion of this quantity, but it doesn't actually show that the coefficient is non-zero. The coefficient of this power of log r is a huge mess of integrals involving zeta and the derivatives of zeta, and it's not clear at all that it's non-zero. So there is actually a different argument that shows that you get a lower bound of order. You can get a lower bound of order something like x to the log r, and then 2k, just k minus 2k minus epsilon. And because poles are integers, you know that the pole is 2k to k minus 2k. OK, I'm going to stop here. Thank you. Oh, they should all vanish. I think they actually proved that in their paper. Naimi, Balazar, and Peterman.
So you told us about the Selberg sieve where you have this sum of lambdas squared. Why are you interested in higher moments? Is it to try and understand just the structure of these sums, or do you have some arithmetic applications in mind?
It started as a curiosity that we're trying to understand the anatomy of the integers contributing to these divisor sums, and in general, the anatomy of integers giving the dominant contribution to the Selberg sieve weights. And also, why do we really need to smooth? Because to me, at least, it was not okay. It was more like a dogma that needed some explanation, at least.
It's very common and occurred in your talk too, that the sieve weights are chosen in terms of some fixed function of log d over log r.
Mm-hmm.
Is there some intrinsic reason the logarithmic scale is the best one?
Why you choose a logarithmic? Yeah, because it's a milder truncation. If you truncate using something like f of d over r, this truncation is too sharp, and you're going to end up to this kind of results. Yeah, they do. And you can understand which integers give you the dominant contribution. But for really large values, they will tell you. When it's a log r to some power, they will tell you something, yeah. One more thing to Roger's question is that if you don't take high moments, you will never see this heuristic being confirmed that I described. Because if you take just the square smoothing, one derivative suffices, and you cannot really see this actually taking place, the savings of the logarithms by every derivative. Yeah. Thank you.